Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss phonon spectrum in solids. Let's begin. Generally, we obtain spectrum in an atom. If we consider an atom, then the spectrum we see due to the change in its transition, means if an electron present in the ground state and it goes through that of excited state by absorbing some kind of energy, and when an electron present at the excited state and it is transformed to its ground state by releasing some kind of energy. Due to this transition, means electron transformed to ground state to excited state and also from excited state to ground state, the transition creates spectrum in case of atoms. But here if we prefer in case of solids, that spectrum we obtain due to phonons. So, phonon spectrum in solids. We have already studied that the crystal can propagate all the frequencies. They allow only those frequencies which fall in the allowed band, and these allowed bands are separated from each other by forbidden band. Let me take the graph between omega and k. Omega and k. For the dispersion relation of diatomic lattice vibrations. In case of diatomic lattice vibration, minus pi by 2a plus pi by 2a, that will be the first Brillouin zone. In that of first Brillouin zone, we see two branches, one is acoustic branches, another one is optical branches. That line is the acoustic branch. Acoustic branch. Next, that line with the optical branch. Optical branch. Acoustic branch, that with the frequency range, that frequency is allowed, and again for optical branch, that with the frequency range, in between these frequency range, that is allowed, but in between that frequency range there will be no such allow of lattice vibration, and that range is known as forbidden band. Forbidden band. The crystal can't propagate all the frequencies, as we see. They allow only those frequencies which fall in the allowed band. These are the allowed bands, one allowed band for acoustic, another allowed band for optical branch, and these allowed bands are separated from each other by the forbidden band. Let us see what is phonon. When we are dealing with electromagnetic waves, the quantization of electromagnetic waves is known as photon. Photon. In the same thing, the quantization of lattice energy is known as phonon. The quantization of lattice energy is known as phonon. And it has the energy is equal to h cut omega. H Planck's constant, omega the angular frequency, and momentum p is equal to h cut k, k be the wave vector. Here omega, that is angular frequency, k wave vector, h Planck's constant, and h cut, that is h by 2 pi. Now we have to study how that phonon is responsible for spectrum in solids. In solids, the quantization of that lattice energy is known as photon, and it has the energy, that energy is quantized, and that value is h cut omega, and the momentum is equal to h cut k. So how the spectrum we generate in solids? By using that phonon. Let us see, in that of lattice, each atom is represented just like an oscillator. So every oscillating atom represent the normal modes of the lattice, in which all the atoms of the crystal take part, vibrating with the same frequency. That frequency is omega. Therefore, the energy of a quantum oscillator is En is equal to n plus minus half h cut omega, energy of quantum oscillator, whereas n is equal to 0, 1, 2, 3, that is the quantum number. let we draw a graph by taking that energy of the quantum oscillator that is energy. The graph is looking like when we put n is equal to 0, n is equal to 0, so E naught we obtain half h cross omega. Here E naught we obtain half h cut omega. Next, when n is equal to 1, so E1 is equal to 3 by 2 h cut omega. When n is equal to 2, then E2 is equal to 5 by 2 h cut omega, and when n is equal to 3, we obtain E3 is equal to 7 by 2 h cut omega. That particular graph shows the energy spectrum in linear harmonic oscillator. Energy spectrum in linear harmonic oscillator, and it consists of a set of discrete levels, that are spaced at the interval of h cut omega. In between these two levels, there will be the interval of h cut omega. Discrete level, interval of h cut omega. So the minimum portion of energy that can be required is h cross omega, that either absorbed or emitted by the lattice to obtain the next mode of vibrations. So we write it, the minimum portion of energy that can be absorbed or emitted by the lattice in the form of thermal vibration corresponds to the transition of the normal mode that being excited from the given energy level to the adjacent level and is equal to that energy is equal to h cut omega. Therefore, depending on the intensity of excitation, of the normal mode, the crystal can emit a definite number of phonons. Example: how? That depend upon this. Depending on the intensity of excitation of the normal mode, the crystal can emit the definite number of phonons. Example: if we consider if some mode is excited to the third level, look at that of figure. In that of third level, it has the energy 7/2 h cut omega. Third level, the energy becomes 7/2 h cut omega. It means that, what is the meaning of 7/2 h cut omega? It means that the normal mode has produced 3 identical phonons, each having energy of h cut omega. Look here, if that normal mode has half h cut omega, so there will be h cut omega, then that will be h cut omega. When 3 h cut omega is added to that of half h cut omega, we finally obtain the energy as 7/2 h cut omega. Therefore, each phonon has the energy h cut omega, so it will be required 3 identical phonons is required for this to achieving the energy 7/2 h cut omega. In this way, phonons are responsible for the spectrum in case of solids. There will be the exchange of quanta of energy, that is the quanta of energy in that of lattice vibrations, and that energy is represented by h cut omega. That h cut omega is nothing but the energy of one phonon. In that way, the exchange of phonon needs the spectrum in case of solids. So, here with the help of this video lecture we understand the concept of phonon spectrum in solids, how exchange of energy takes place inside that of solids by taking phonons. On that of phonon we explain how spectrum in solids. So, with this useful and informative notes, let me wind up this session. Thank you.